In this tutorial, we will be discussing the duality of light. An object gains and loses radiant energy by either absorbing or emitting radiant light, radiant energy. Radiant energy is absorbed and emitted through discrete packets called quanta, so small amounts of energy. Radiant energy is proportional or directly related to the frequency. We learned previously that this is Planck's constant, so we're going to multiply the frequency by Planck's constant. This also means that it's inversely related to the wavelength. So, the larger the wavelength, the smaller the frequency. It has a smaller energy. The shorter the wavelength, the larger the energy, because it has a larger frequency. Frequency is also equal to c over lambda, and that's where the inverse proportionate comes in. So let's talk about the duality of matter. From deBroglie's investigation, the relationship of mass and wavelength, he proposed that all moving objects have wave properties. We learned from Einstein E is equal to mc squared. M is the mass, while c is the speed of light, 3.0 times 10 to the 8th meters per second. We also learned from Planck that the energy is Planck's constant times the frequency. We can set both of these energies equal to each other. So mc is equal to h over lambda. So the mass times the velocity is equal to Planck's constant divided by lambda. deBroglie's experiments led to the idea that particles could have a wave-like character. So the wavelength is equal to Planck's constant over mass times velocity, which is the previous equation rearranged, where the units of wavelength is in meters, Planck's constant is kilograms meters squared per second squared, the mass is in kilograms, and the velocity is meters per second. He predicted that a wavelength of a particle is inversely proportionate to its momentum. Because electrons are so incredibly small, their wave character or their wave behavior is rather significant. Proof of the wave nature of an electron came a few years later with the demonstration that a beam of electrons would produce an interference pattern as the electrons were waves. So if we look at these two pictures, this is on the top as if electrons were particles, whereas the bottom is if it is in real life. If electrons behave only like particles, there should only be two bright lights where those slits are. However, the reality is electrons actually present an interference pattern, and we've seen this in previous tutorials where the waves diffract and then overlap again, where they have one area that's bright by the waves converging and one area that's dark where the waves cancel out. And this means that they're behaving more like waves. So let's take a minute to solve another energy question. Calculate the energy associated with 1 mole of photons of green light, which is 555 nanometers. So we need the energy equation. Energy is equal to Planck's constant times the speed of light over the wavelength. However, because the speed of light, 3 times 10 to the 8th, is in meters per second, that means we need the wavelength in meters before we can go on. So 555 nanometers over 1. Nano means 9. So 1 times 10 to the 9th nanometers is equal to 1 meter, which means 5.55 times 10 to the negative 7 meters. Now the energy is then Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, times the speed of light, 3.0 times 10 to the 8th meters per second, and the seconds cancel, all over 5.55 times 10 to the negative 7 meters. This then equals, the meters cancel, 3.58 times 10 to the negative 19, and this is the amount of energy per photon. Now we want an entire mole of photon. Remember, moles is just a system of counting. So even though we're talking about photons here and not atoms or ions, it's still going to be 6.022 times 10 to the 23rd. But now we're just going to use photons is equal to 1 mole. Alright, so we have 3.58 times 10 to the negative 19 joules over 1. We have joules on top, so we'll put joule, 1 photon. We want to actually have joules at the end. So this is going to be a little bit different just for this matter. We actually want to get rid of the photons and have moles down there instead. Photons are on top, so we want it opposite. So photons on bottom, so photons have to be on top. So 6.022 times 10 to the 23rd, and that is 1 mole. The photons cancel, now we have joules per mole. Multiply that across, and it comes 2.16 times 10 to the 5th joules per mole this time rather than photons. And that explains the duality of light, plus giving you another example of energy.